Okay. So maybe maybe the calculation is a little bit quick. So let me just recap what the hell is going on. Right. So remember that we just write our ax0 as ax at a equals to ax0 and ax1. So this ax0, remember that we have identity, right? Or basically spectral decomposition in a linear algebra. Ax is a Hermitian operator. So this ax0 are basically the projector to zero, or basically projector to one eigenstate, right? So remember, this is a projector to eigenvalue 1, but that's a map to 0, one eigenstate. And there is a guy which is ax1 dot 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 dot, same. It's basically the -1 eigenstate. Okay, and also this bx0 and the bx. And we also have the resolution identity, right? Two projectors, because your vector space is a span of, because Hermitian, right? So it's all remember when operator is Hermitian, then all the eigenvectors span into the whole subspace, right? So this means the identity must equals to the whole projectors. This is the resolution of identity. Okay. So this is why I can combine these two and then write my ax0 equals I identity plus a x divided by 2. And my ax1 is basically identity minus ax divided by 2. Okay, so this is the key calculation. Just this is just the change of variable, right? And what we say is that remember that probability of winning is basically 1 divided by 4, because there are 4 kind of situation, and then we just sum over the possible x and y, either 0 or 1. And then we also we care about win, right? So it's a x squared b, x and y. And then we just get the probability, right? So it's basically, so it's basically this. Your state psi and your state psi, and you get a projector, right? So it's ax, a. So you use ax as projectors and tensor product with b, y, b. Good. Okay, and as we just did calculation, let me just quickly write down it again, and hopefully so x and y, when x, y equals 0, what do you get? You get a 0. So this x and y is 0, right? So the condition is that a is 0 or b is 0, or a is 1 or b is 1, right? So it's a 0, 0, b 0, 0 plus a 0, 1. Sorry, 1, b 0, 1. Okay. So this a 0, 0 is half 1 identity plus a 0, and identity plus b0 plus 1, right? So 1, whenever you see 1 is minus 1 minus a0, 1 minus b0. And all this a0 and b0 they cancel, so you get a0, b0 plus identity divided by 2. This is the calculation that we just showed. Simple algebra, right? Okay, and when x equals to 1 and y equals 0, so x and y are all 0. The same, right? So this term, this calculation here will be just a 1, and the b0, and then you get 0, 0, or 1, 1, right? The same calculation. Because here that the x exclusive OR is still 0, right? So either they are all 0 or they are all 1. So same reason is identity minus, sorry, it's identity plus a0 divided by 2, And it's still 0, T0 here. So it's half of identity plus. So this is 1. And then this is identity minus A1 and identity minus B1. Sorry, B0, right? B0. Because this is B01. So it's the same identity plus A1 B0 divided by 2. And due to the symmetry that we don't need to do calculation again, we know that x equals 0, y equals to 1. We just exchange A and B. So the calculation must give us identity plus A0 B1 divided by 2. So we finished 3 different sets of conditions, right? 1 and 2 and 3. So the first case is basically the same thing, right? So x equals to 1, y equals to 1. Then we get A1 and a B1, or A1, B1 plus. No, they need to be different, right? So it's 0, 1, or 1, 0. So identity plus A1 minus identity minus B1. And this is identity minus A1 and identity plus B1 divided by 2. So it's identity minus A1 B1 divided by 2. Okay, so we get one plus sign and 3 minus sign. We got, sorry, what the hell is going on? So we got, right, we got 1 plus sign and this, sorry, 3 plus sign and 1 minus sign. Okay, so here. Okay, so the probability that we win is basically 1 divided by 4 with sum over the 4 contributions. So it's half of A0 B0 plus A0 B1 plus A1 B0 minus A1 B1. Right, and there's a 4. Because each of get sorry. Here, right, 4 0. 1 1 1 1, right? 1 1 1, right? Good. So we can write as a 2 probability of win minus 1. It's basically 1 divided by 4, A0 B0 plus A0 B1 plus A1 B0 minus A1 B1. By the way, I forget about this side. So the probability of winning is that's equal to 1 plus the Bell expression, right? Divided by 2. And it is 1 plus 2 square root of 2. Sorry, there's 1 divided by 4, 4 half. Okay, so it's 1 plus square root of 2 divided by 2 half. So this is 85%. Good. Oh, you can just try to like go online. I just did it. You just do Google and the calculation, just do this, and you get 85%. Okay, so this is all the CHS again, essentially. So let me just tell you why this is important. So this is a weird implication. So that means that if you are a guy, which you're a referee, right? And there are 2 parties, and they claim that they have quantum like entanglement between them. How do you check it? So previously we said Bell inequality, right? But we didn't give you like the operational way to check whether 2 parties has entanglement. But now you can play this CHS again with them, right? So if they have no quantum entanglement, if they have no quantum, then they can only win less than equal to 75%. But if they have quantum, they can win 85%. So this is supremacy. Something somehow like, so you should be like very, very like, I don't know, because when I don't know what kind of like, if the first time you heard about quantum computation, that it's not obviously that you can construct any like mathematical rigorous example such that you know quantum can do better than classical. I mean, at least mathematically, right? You can hear some news. People say that if you have quantum computer, you can do A to B to C, but you're not like easy to see something that, oh, I write down some example that I show that classical cannot can only do something, but quantum can do better, right? But this should be the first example that you see that quantum can beat classical, that mathematically that we show. One is 85% one. But okay, so so this is the thing. And the third thing is that they require let me say this. So this CHS game is just one example of non-local game. So you might think that is there a way to like design like more sophisticated, right? But like for example, mathematicians are crazy, right? There may be a way to design some sophisticated non-local game such that the quantum can always win probability one, but classical cannot. So there exists a game called Magic Square. So I will just write down some keyword, but if you're interested, you can go to chat. So there is a game called Magic Square. The quantum can win probability one, but classical can only win at 77. I think 17 divided by 18. And there are more sophisticated one. It's called Pauli braiding test. There are some parameter n here, and I think quantum you can win that with probability one. But for classical, that if you choose n to be large enough, and there's no way for classical to win. So the winning probability for classical is like arbitrarily small. Well, that means that if you extend this CHS game to very exotic one, you can create some very like weird non-local game that if two guys have entanglement, they can win probability one. But if two guys are both classical, then they have no chance to win. The probability they're winning is arbitrary. So this is give you the like you can like somehow like use this to check the entanglement. But there are some the thing I want to say is that but in order to do this quantum supremacy C, right? You need two quantum device, or I should say like from my understanding that I should say you need two quantum devices. So that means that if you want to if there is a two like powerful quantum computer in this universe, then you can do these experiments and somehow like you can show that you can be classical one. I can because you can like one of that you just separated. You just give two quantum computers to two guys and then play this CHS game, and then they will like they can beat classical, or you can do much more sophisticated. But you need two quantum devices, right? One is for Alice, one is for Bob. But what if you only have one? Let's say you have only one quantum computer at your home, and you cannot use this non-locality, right? There's no non-local game you can do. Right? So can you still find something which is quantum easy What classical hard? This become like the good. This is become like the the next question, right? Because I have two content, then I can do this non-local again. But I have only one content, then how then there's no way that I can enhance this non-locality, right? But classical. So this is somehow this is why we need to like in the next okay 6 weeks. Hopefully we will like those do some quantum. So this is why we ask what people ask about this. It's a quantum computation, right? Because you only have one quantum computer, so then you need to design. You need to find a more sophisticated mathematical object or question such that you hope to prove rigorously that quantum can be classical, right? Similar to this non-local case. So this is why people need quantum computation. And you will ask, maybe let me just tell you, and you will ask, can we have uh the basic evidence or example, right? This is CHSH example. Can you have a solid example that one can show quantum is bit classical, right? Can we do this solid example? And the answer is sort of. So it's like sort of is like we have some evidence. So evidence means it's not rigorous mathematical proof, right? But there's a way to make it rigorous. But we don't have the unconditional proof. Or basically we can say we think it's true under some assumption, some mathematical assumption. So this is the rest of the whole course. But tell you why how do you like change to one quantum computer if you don't have two? Actually, right, in this situation, again, you don't need to do any computation. The only thing we need is that Alice and Bob have two qubits, and then they can do the measurement. They don't have they just need two qubits, right? They don't need like 100 or 1 million qubit or whatever, like very large devices. But if you only one quantum computer, it becomes like difficult to like develop some tool to analyze this situation. So we think it's true under some mathematical assumption. And people are like believe this is true. Okay, so it's not yet finished. It's weird. Okay, so this is many like there are like 20, 30 years research after this CHSH. So this also tell you something, right? This tell you that there's a when you have two quantum computers, they are separated than one classical guy. So this classical guy is this referee, right? Referee send 2 bits is classical guy. This C guy, right, has no quantum power. Right, this C guy has no quantum power, right? The only thing this C guy can do is just send 2 bits, X and Y, right? So C has no quantum power, but he can detect. He can detect the quantum, right? He can detect the quantum entanglement. So that means that if Alice and Bob claim that they have a quantum computer, C can check it, right? So C can check. If Alice and Bob claim they have quantum. Okay, so this is practical, right? Suppose that there are two countries. They claim they have quantum computer. Then C can play this game with these two countries. And if they win with this game if that's greater than 75%, then I was forced to believe that they have quantum. But the open question is that how do you do this if only one? So what I'm saying is that if there are so for example, like United States or whatever country claim that they have quantum computer, and then no other country has quantum computer. How do you detect they really has a quantum computer? Okay, so really they really have a quantum. So that means that let's say you're a country, let's say X, right? So X claim uh uh it has quantum power, but you're a classical guy, right? You are not quantum. So how do classical guy detect? Oh, by the way, there are much more open questions here. But oh, by the way, these are some of them are research topic that recently got solved. I think these are recently got solved. But still also need to do some like mathematical assumption. Okay, and yeah, so before we do this, before we go to next topic. Oh, by the way, so I owe you guys. There's a so-called rigidity. So let me talk about this. So there is an idea called rigidity. So rigidity tell you that. So let me just say in like say informal version. The formal version I will try to give you maybe tomorrow or next week. So informal version just tell you that so if Bell reach the 2 square root of 2, the states is almost is somehow like close to the Bell state. So this close means that because Alice and Barb they can do arbitrary small unitary rotation, right? So the states may not be written as 0, 0 plus 1, 1, maybe 0, 0 minus 1, 1, but different basis. So actually there are Bell state but up to a local transformation. So this is called rigidity. So this means that if you get to square root of 2, then the state must be a Bell state. But this gives you a really weird conclusion that if someone win this CHSH game with 85% probability, they must have Bell state. They must use Bell state. Right? Is it obvious? Because the probability of win is through probability. Win minus 1 is bounded by Bell state. So if they win with the maximum probability, that state between them must be Bell state. And moreover, they need to use a set of they need to use a set of fixed measurement up to local symmetry, right? So the measurement they use must be fixed, like up to some degree of freedom, right? Up to some degree of freedom. So this means that this classical guy, he plays the game. But this game actually restricted two powerful guy. Restricted. Like two powerful Alice and Bob. So you can imagine that if Alice, even though Alice and Bob, they have arbitrary computational power, they can solve housing problem or they can solve anything. They're like ultimately godness, right? They are like not human or something. If they need to win this game with maximum probability, they are not allowed to do anything special. The only thing they can do is just have a Bell state and play the same measurement rules. So you are a classical guy which can only send two bits. But playing this game will allow you to force these two untrusted provers. They do something very special just to win a game. So this is hopefully you feel like this is very weird, right? So these two are, so let's say I give you two untrusted provers. One is called Alice and Bob. They are like ultimately powerful. They can do anything. But once you play this game with them, then there's no way they can win with higher than 85%. If they win with higher 85%, the rigidity will force they have the Bell state. And the force they do the same calculation. So the rest of probably tomorrow is just, or this this week just tell you that what's this rigidity. So before I finish, I want to introduce a one linear algebra lemma that probably you know or you don't know, but this is what I call the abstract qubits. Maybe other people will not talk about this, but I think it's interesting. So this is linear algebra fact. Okay, so the proof is simple. I will use words. Okay. So let's say V is a complex dimensional some vector space, and then let's say you find two operators looks similar to Pauli, right? So suppose there exists X and Z. By the way, these are not Pauli. These are just looks like Pauli. I just use X and Z, so I use tilde, X tilde and T tilde such that their Hermitian, and the square is 1, very Pauli, right? Looks like Pauli X and Pauli Z, and then their anti-commutes. Then there exists the basis. Is this a basis such that there are exactly Paulis? So there is a unitary, or actually there will be small subspace to Pauli, right? So there's a unitary U from V to V, such that for U X tilde U is equal to standard Pauli X. So standard Pauli X tensor some auxiliary vector space. So that means that let me just, how should I say this? Right. So maybe I use this identity and U tilde U. So that means that okay. So let me just write this. So if you have like two Hermitian operator, they square equals to 1 and their anti-commutes, then this original vector space is even dimension, and this vector space can be isomorphic to the small subspace, which is two-dimensional tensors on auxiliary dimensional D space. And then is this a unitary such that is U X tilde U dagger is the standard Pauli X with the so this identity. Okay, identity on dimension D. So this means that if someone asks you what is the qubit, mathematically this is a qubit. Mathematical is that you take any vector space. If you can find two operator which is square equals to 1 in that commute Hermitian, then naturally this dimension must be even. And then you can factor the original vector space to tensor product of small qubits. You can extract one small qubit, tensor with the others. Is it this theorem obvious? Okay. Okay, so one interesting question for you this is open question. This is what I'm trying to prove. So one open question is how do you generalize? How do you generalize theorem? Generalize this one. To like so-called qubit. This is an interesting topic. Oh. So I don't have time, but I can first easily show that dimension must be even. Okay. So so let me just quickly prove that dimension must be even. Dimension must be even. So this is simple linear algebra exercise. So notice that so let's say Z squared is 1, right? So that means that eigenvalue of Z can only be plus or minus 1. And what's the trace of Z tilde? Basically trace of Z tilde X tilde squared, right? Because X squared is 1, and then it's also trace of the X tilde this, right? And then trace of minus. So I just exchange these two, right? because Z and I say that Z and X are anti-commute. But trace is cyclic. So it's -1 trace of good. So it's cyclic. So this is minus trace of Z tilde. So trace of Z tilde is the same as trace of Z tilde. Minus. So trace of Z tilde must be 0. Right? Since it's 0, 0 must be sum of the eigenvalues. So sum of the eigenvalues. But eigenvalues is either plus or minus 1. So you get a bunch of eigenvalue which sum 0 and one of is either one of plus 1 or minus 1. So it means that you must have equal 1 and the equal -1. Right? Equal 1 or equal -1. So the dimension must be even, right? Dimension is just the sum of the number of eigenvalues. But you get either 1, the same 1 or -1. So you get something. Okay, and the rest let me just use words. So Z is Z, this Z, right? This Z is Hermitian, right? So there's a basis such that I can make it diagonal. But I know that the number of is either like 1 or -1, right? So there exists a basis that I can write Z tilde as something like this. Right? Because I can collect all the one basis. I can collect all the eigenvector with corresponding eigenvalue 1 into a subspace. And another to be -1 subspace. Okay. Or simply that I can write my vector space into the basis, either it's called 0 EI, so I from 1 to D, or like 1 EI, like I from 1 to D. And the Z of the tilde of 0 EI will just be 0 EI. And the Z tilde of 1 EI will just be -1 EI. So this statement is the same as it's exactly the same as I write this Z tilde into this basis. It's the same as I write my vector space. Dimension is even. I collect I separate both two parts. One part with eigenvalue 1, one part with eigenvalue -1. And the Z icon, one part will just proportional to one part and this. And obviously the X anti-commutes with Z tilde, right? So X must send the eigenvalue 1 subspace to eigenvalue -1 subspace because X tilde anti-commute with Z tilde. So anti-commutes. So X tilde will just shift or just change from 0 to 1 and then 1 to 0. So if you write everything I say into rigorous mathematical notation, that basically you prove this theory, right? This theory, what this theory says is what I just said. There exists a base, so you just separate Z into +1 and -1 basis. So there's exists a U such that U Z tilde U dagger is this one. And the X anti-commute with Z, so X must send the eigenvalue 1 to eigenvalue -1 and send eigenvalue -1 to eigenvalue 1, send it back. So it must be exchange. Okay, so this is called this abstract QB lemma. Why we need this? Because let me just spoiler. So spoiler is that we will show that if Bell reach the 2 square root of 2, we will show that A0 and A1 must anti-commute. So I will show you tomorrow. And the B0 and B1 must anti-commute. And this will force, by that previous lemma, this will force that A0 and A1 must be X and Z. And this will force that the middle state must be locally unitary to Bell state. So which will finish the proof. Maybe tomorrow. That's it. Thanks. 提早下课，反正也讲不完，下礼拜讲。有任何问题来问，有什么问题就记得明天要交作业。作业如果太难，跟我讲，应该不会难。 把这个，不然你的声音就会进去。